Hello everyone, welcome to lecture 1.1, Representations of Chemical Substances. This is the first lecture for the Chem 105 series, and in this lecture we're going to talk about the different ways that chemists think about and communicate about chemical substances. It's not a particularly difficult topic, but I do want you to take it seriously. So, please, if you have not already done so, please turn off your cell phone, close your Facebook. I'll give you a minute to hit the pause button, take care of all of those things, and when you're done, unpause and we'll continue. So let's begin with representation. What do I mean by representation? Representation really has two basic definitions. The first one is a mental image or construct based on your experiences about some kind of an object or an idea. For example, if I were to say the word airplane to you, you probably would get an image in your head of something with wings and a tail. You'd know it's flown by a pilot. You can use it to travel. If you've traveled by airplane, you may have some memories that all kind of mix in to your idea of what airplane means. And so that combination of all those different experiences is your mental image or your representation of an airplane. Also, a representation can also mean can refer to a physical object that stands for something else. So for example, to continue with the airplane idea, the photograph of an airplane is a representation of an airplane, and a model airplane or a toy is also a representation of an airplane. And in fact, even the word airplane is a representation of airplane because that word triggers all of these other ideas. So how do we apply this idea of representations to chemical substances? We can take the ideas of mental constructs and physical objects that represent something and combine them together and say, for example, that representations are ways that we experience, think about, understand, visualize, symbolize, or name chemical substances. And for chemical substances, these representations are going to break down into three basic types, and it's important to talk about those. So we'll look at each of these three. First is macroscopic. The second type of representation is microscopic. And the third one is symbolic. And we're going to look at all three of these in turn, starting with macroscopic. So a macroscopic representation of a chemical substance is basically your collected experiences with that substance. This representation may include, but is not necessarily limited to, how that substance looks, feels, smells, or tastes, whether it's heavy or light, perhaps dense is a more appropriate word, whether it's hard or soft, is it malleable or brittle? If you bang on it with a hammer, does it bend or does it break? Also the physical state. Is it typically found as a solid, a liquid, or a gas? And another one that's very important is what is it used for? Or where might you encounter this? How do you use this substance in your daily life? Next, let's look at a few examples. We'll start with a fairly simple and familiar example, water. To the right, I've collected a few images that indicate some of the ways that we typically interact with water in our everyday lives. And I also took a moment to write a short little paragraph about water. Water is a colorless, odorless liquid. It has moderate density. Some things, like wood for example, float on water, while most metals sink in it. It's essential for life. Not only do plants and animals need water to survive, many actually live in water. It comprises a significant fraction of the body mass of most living things. It's found in lakes, rivers, clouds, and oceans, and about 2/3 of the Earth's surface is covered by water. Now, that's not necessarily a definitive example of a macroscopic representation. There are other things that another person might have said differently, in addition to or instead of some of the things that I've written here. And any of those are fine. Anything that essentially encapsulates your collected experience with water would make a good macroscopic representation. Okay, let's take another common example, sugar. But this time, instead of me putting down my representation, I'd like you to spend a minute or two thinking about sugar, and then in your notes, go ahead and hit the pause button, and then in your notes, jot down a couple of your impressions about sugar, some things that may comprise your macroscopic representation of sugar, and then when you're done, unpause, and you can take a look at what I've got. Okay, so here are a few pictures, some of the mental images that come to my mind when I think about sugar. And a couple of the things that you may have written down is that it's a white crystalline solid, it's soluble in water, it's used to flavor drinks and foods, it has a sweet taste, it provides energy, but too much of it is unhealthy. And again, your macroscopic representation may have included, there are several things you may have included that were not on my list, and that's fine. And to take another familiar example, I'll just quickly mention salt. I've got a couple images on the right again, and if we want to talk about some of the concepts that make up our macroscopic representation, we might say that again it's a white crystalline solid, just like sugar. The crystals are cubic. If you look at the picture on the right hand side, you can see they make really nice, essentially perfectly cubic crystals, which are very nice. It tastes salty. That's a bit of a tautology, but I really can't think of any other way to say that. Salt is soluble in water and is found dissolved in the oceans. And I want to call your attention to this last one, because we may come back and revisit this. Salt solutions, when you dissolve salt in water, the solution can then conduct electricity, which is not true of sugar. And so that's an interesting characteristic of salt. We'll have a chance to revisit that later. Next, let's look at the second type of representation, which are the microscopic representations. Microscopic representations involve the composition and structure of a substance on the atomic scale. And this is generally below our level of experience. So this is not the way we see things every day. This is based on what we infer from chemical measurements and experimentation. Some of the things that comprise this microscopic representation are which elements the substance is made of, how many atoms of each element are there, how those are connected or arranged in space. In other words, what's the molecular shape? What's the nature of the connection between the atoms? There are a lot of different ways that atoms can be connected. That's a topic for later on in the semester, but that's an important part of our representation. And what's the distribution of electrical charge? Even molecules that don't have a full positive or negative charge can sometimes have asymmetric distributions of electrical charge, so that they have regions of partial positive and negative charges. And that can be an important part of our microscopic representation. All right, here are some simple representations of water, microscopic representations of water. This first one is what's called a Lewis dot structure. You don't need to worry too much about that right now. Although I will say Lewis dot structures are extremely important. We're going to be talking a lot about those at the end of the first semester, probably in November and December of the first semester. We'll spend a couple of weeks on those. Basically, this is just showing that a water molecule is composed of an oxygen here connected to two hydrogens. Okay. Look at the one below that here, which is called a ball and stick model, because the atoms are drawn to have a little bit of three-dimensional space to them, so they look kind of like balls connected with sticks. In this one, I've also indicated the bond angle here of 105 degrees, or a little bit less than 105 degrees. And what's not indicated, but could be, is the fact that this molecule has a bond length here of just under 1 angstrom. And all of that structural information is an important part of the microscopic representation. We can also look at this one here, which is called a space filling model. Because it shows you in a little bit more three-dimensional accuracy the volume that's actually occupied by those atoms in the molecule. That's basically, if you really could see the molecule close up, that's kind of what it would look like, we believe. And down at the bottom, this one down here is really interesting. The blue and red that you're seeing on this one is kind of a electron density map. And the blue region is showing you an area where the molecule is slightly electron deficient. So the electrons in this molecule have been shifted from this end of the molecule up to this end. And what that does is it creates a region at the bottom of the molecule which is slightly electron deficient, and because electrons have a negative charge, this electron deficient region now has a slight positive charge. The region at the top, which has an excess of electrons, then has a slight positive charge. And I'm using lowercase Greek delta to indicate a partial charge rather than a full charge. Pen's not working very well. But this electron distribution is an important part of our microscopic representation of this molecule. It tells us not just how the atoms are connected, but where the electrons are and where the molecule has regions of positive and negative charge. So the positive and negative charge are really going to impact how this molecule behaves, how it interacts with other species, whether it's soluble or insoluble, and some of its chemical properties as well. So that electron distribution is an important part of the microscopic representation. And the last one over here is a microscopic representation of bulk water. So this might be a representation of a drop of water or a beaker full of water, and this shows how all of those water molecules would interact with one another in that bulk solution. Now, there's something about this which is a little bit odd and a little bit funky. This isn't extremely important, but I want to make something clear. The pictures that you're seeing here are not really the microscopic representations. The pictures are actually representations of representations. Okay? The microscopic representation of water is the collection of ideas that encompass all of this, right? So the microscopic representation of water is the atoms involved, how they're connected to one another, as we see here, the bond angles, the bond length, the way the molecule occupies space, the electron distribution, and how the molecules interact with one another. All of that together comprises the microscopic representation. We've got 5 different images here to show all of those. But if you take all of those things and merge them together, that combined idea is the microscopic representation of water. In continuing, we can look also at a microscopic representation of sugar. The image on the left is a Lewis dot structure. The one on the right is a ball and stick model. In both cases, they're showing all the different atoms and how they're connected to one another. The one on the left is a little bit easier to read. The one on the right shows the atoms in a little bit better geometric detail. So depending on what you're talking about, either one of these may be preferable in a given circumstance, but they both are nice microscopic representations for sugar. All right, salt. We talked about salt before. We have talked about our macroscopic representation. Our microscopic representation might contain some ideas, like the idea that salt is formed when sodium atoms transfer an electron from the sodium to the chlorine, And because electrons have a negative charge, when this electron moves from one to the other, the sodium takes on a positive charge, the chloride takes on a negative charge, and so you get a pair of ions, a positive sodium and a negative chloride. And if you have a whole bunch of these, they stack up and they make this very nice, neat, orderly arrangement, which is the basis of that sodium chloride crystal. Okay. Now, symbolic representations are the last of the three that we're going to look at. Symbolic representations are really important because these are the ways we communicate with each other. Symbolic representation are the names and symbols that we use to communicate information about substances, reactions, and processes. And much like the microscopic representations, they typically contain a lot of the same information, which elements the substance is composed of, how many atoms of each element there are, the physical state of the substance. And this is kind of interesting because this particular property that we're conveying here, this is something we typically think of as being related to the macroscopic representations. But we can also include this in our symbolic representations. And how many molecules of each substance are involved in the process. We'll see what that looks like in a minute. Let's take some examples. All right, we can look at water, which is a simple molecule, as we've seen before, containing one oxygen atom and two hydrogen atoms. The name of the molecule is part of the symbolic representation because we use that to convey information when we're communicating with one another. So the name water is part of the symbolic representation. We can also write what we call a chemical formula for this. And for water, this would be H2O, indicating two hydrogens and one oxygen in the molecule. Now, this number here is called a subscript. And that's important. A subscript in a chemical formula tells you how many atoms of that element are in the molecule. All right. We can also, if we want, we can indicate the state of the substance. So if we're talking about liquid water, we can include an L at the end. If we want to talk about ice, we can write this as H2O solid. And for steam, H2O gas. And in most cases, it's important to include those states with the symbolic representation. There may be some instances where it's less important, but generally we're going to try to include those all the time. Okay. We can take a look at the sugar molecule. Now, there are actually a lot of different kinds of sugar molecules, and the particular one that you're familiar with that shows up on your dinner table and the one you put in your coffee has a special name to organic chemists. It's called sucrose. Okay, so this is part of our symbolic representation for this. We give it this special chemical name. We can also write a molecular structure, as we did before, and for sucrose, C12H22O11, which means if we go through and count all of these, there are 12 carbon atoms, 22 hydrogen atoms, and 11 oxygens. All right, and this one is salt. You can see here's our macroscopic representation. This is our microscopic representation, showing that it's composed of sodium and chloride ions. And we're used to calling this compound salt, but in chemical terms, the word salt is a general term. There are actually several different kinds of salts. This particular one is called sodium chloride because it's composed of sodium and chloride ions. So this name, again, is part of our symbolic representation because we can use that name to to suggest or imply or symbolize all of these different representations. And we can also write a chemical formula for sodium chloride by writing Na for sodium, Cl for chloride, since there are one sodium and one chloride in the crystal, or a 1-to-1 ratio, I guess I should say. And generally speaking, sodium chloride, unless we get it very hot, is going to be a solid. So we'll indicate the state as well. We can also look at symbolic representations for ions. We hadn't done this yet, but this is a sulfate ion. You can see that it's composed of one sulfur atom and 4 oxygens and 2 negative charges. So the sulfur ion has a charge of -2. For our symbolic representation, we include, as always, the name, since that's one of the ways that we communicate when we talk about sulfate ions, is using the name. And we can also write a chemical formula for it. In this case, since there's 1 sulfur and 4 oxygens, we write the sulfate ion that way. Okay? And remember that this is our subscript, indicating that there are 4 oxygens for every 1 sulfur. Okay? And to this one also we're going to do something else. We're going to add a superscript, 2-. In this superscript, the superscript tells us what the charge is. Okay, so that -2 up here says that this ion here has a net charge of -2. We can use these symbolic representations to describe processes like the boiling of water. So I've got water going from the liquid state to the gaseous state, which we write as a chemical equation. We can use a symbolic representation to indicate chemical reactions, and this is a fairly famous one. The Hindenburg, as you probably know, was burned up, and the reason it burned up was because in order to keep it afloat, it was filled with hydrogen gas. And hydrogen gas is lighter than air, makes the blimp very light, but unfortunately it's also flammable. And so the hydrogen can react with oxygen to make water, a very energetic reaction which also produces a lot of flames. In this reaction, though, there's something special that I want to call your attention to, and that is these numbers here. Okay. And these are numbers, notice that these are different than the subscripts and different than the superscripts. These are numbers that are written in front of the molecules, and these are called stoichiometric coefficients. And what stoichiometric coefficients tell us is they tell us how many molecules of each species is required to complete the reaction. So what these numbers here are telling us is that 2 molecules of hydrogen react with a single molecule of oxygen to make 2 molecules of water. And by convention, if we've only got 1 molecule of oxygen here, we usually leave that space blank. But an empty space there should be interpreted as a 1. We typically leave the 1s off, so if you don't see anything there, you can assume that that's a 1. And here's another chemical reaction. This is one that people love to do because it's really violent. It generates a lot of heat, and also one of the products that it produces is hydrogen gas. And hydrogen gas, as we saw in the previous slide, is flammable, so this creates a lot of heat, and then the hydrogen gas lights, so you get these giant flames, which is kind of neat because the whole reaction takes place in water or on top of water, so you wouldn't really expect flames. But if you throw a hunk of solid sodium into a beaker of water, it reacts to make potassium hydroxide and hydrogen. And as I indicated before, the generates enough heat that the hydrogen bursts into flame. So it's a really fun reaction. I want to point out also that in this one we've got some stoichiometric coefficients. So 2 atoms of potassium are required to react with 2 molecules of water to make 2 molecules of potassium hydroxide and 1 molecule of hydrogen. And also note that we've got states. In this particular reaction, we've got 4 different states indicated here. The potassium is a solid, the water is a liquid, the hydrogen is a gas, and this one I'm not sure we've mentioned yet. We'll look at this in one of our subsequent lectures. But this AQ means aqueous, or dissolved in water. So this potassium hydroxide, as it's formed in this reaction, it immediately dissolves in this water here. Okay, we've spent a lot of time on this subject, so I think it's a fair question to ask, what's the point? And there really are 2 points to this. The first one is integration. And by that, what I mean is that all 3 of these, even though we've discussed them separately, should really be thinking about all 3 of them together simultaneously. We tend to kind of compartmentalize these and think of the macroscopic representation, the microscopic representation, and the symbolic representation separately. But they really do all belong together. And the difficulty sometimes of putting them together and thinking about them at the same time is part of what makes the next slide so funny. This is one of my favorite internet photo jokes. And the best way to make something really funny sound really unfunny is to try to explain it. But I think what's interesting about this is what's really happening is we're putting a microscopic representation where we expect to see a macroscopic representation, and that just kind of sends your brain into all kinds of convulsions, and it's amusing. All right, so the first point for these, discussing these 3 representations is that you need to integrate these. And so whenever you hear, for example, the word water, or see the formula H2O, you should immediately, and importantly simultaneously, think of both of those representations, because that's what's really important here. And that kind of leads us into the second point here for discussing these 3 representations, and that is to focus on the chemistry. And this is something that's so fundamental, it's often easy to overlook. Now, this symbolic notation is very compact and efficient. Using the symbolic notation, we can convey a lot of information in a very small amount of space. So in chemistry, we almost exclusively use this symbolic notation. We write chemical formulas to represent substances. We write chemical equations to represent processes. But this really is not what's important. Okay, this is really just an efficient tool, okay, for representing this, which is the chemistry. And so even though we're going to spend 90% of our time writing things in this format, what's really important is this part up here. And so you really need to focus on this. If you spend all your time worrying about how to move your symbols around and where does the 2 go and where does the 3 go and is this a subscript or a superscript, those things are important, of course, but you can spend a lot of energy dealing with those things without really actually getting at the chemistry, which is the important part. In fact, I think we could say that the science of chemistry is really all about trying to understand the macroscopic properties of matter as a consequence of their microscopic structures. So understanding water, by understanding what that microscopic representation is, the size and shape and electronic distribution of those water molecules, we can use that to explain the macroscopic properties of water that we see. And that's really the whole point. And that's really where your attention should be focused throughout this semester. I'll show you an interesting example of that. All right, this is Democritus. He was a Greek philosopher that lived about 2,400 years ago. And he was one of the founders of the atomic theory, one of the first people to say that matter is composed of atoms. And he had a lot of interesting theories about how the atoms worked, one of which was this. He said some atoms have sharp points on them. They're kind of jagged and pointy. And these things, when you put them in your mouth, the things with hard-edged or sharp atoms have a bitter taste, like lemon juice would be an example of something that he would say probably is composed of sharp, pointy atoms. On the other hand, there are some things that have round, smooth atoms, and when you put those in your mouth, they kind of roll around pleasantly on the tongue, and they have a sweet taste. So things like sugar and honey and things like that would be composed of smooth, round atoms. Now, the first important thing to say about this is that this theory is not true. Things are not composed of sharp atoms or round atoms. So this is not a correct way of describing sweet and bitter taste. But he really was onto something here. And what he was trying to do is extremely important. And what he was trying to do with this explanation is suggest microscopic properties of substances which could be used to explain our observed macroscopic properties. Okay, so using the shapes of the atoms as a way of describing the properties that we experience. And this really is what chemistry is all about. This is what we want to do, and this is what we want to focus on. Even though his particular theory was a little bit, seems kind of silly to us now, what he was doing was really fundamentally important and really kind of remarkable. So your goal in this class ought to be, when you're confronted with an equation like this, and we're going to look at a lot of things like this, and we'll be doing math problems based on these, and all of these numbers are going to end up being important. But instead of focusing only on these numbers, when you see an equation like this is methane reacting with oxygen to make CO2 and water, you should immediately be thinking, what's really going on here? And what's going on here is, this is a way of explaining the combustion of methane in a Bunsen burner. So you should immediately be thinking of this macroscopic event that you can witness, and you should also be thinking of the atoms that are involved, their shape and their reactivity, and why these atoms and molecules give rise to this reaction. That's what's ultimately important. And so you need to be thinking about these two things while you are looking at this. This, of course, is important. We don't want to ignore that completely. But we don't want to think about this up here to the exclusion of the interesting stuff down here. All right, everyone. Thanks for sticking with me through this first video. So what should you be doing now? What you ought to do, hopefully you've taken good notes through this video. Go over your notes, read through them, see if you have any questions. Recopy some parts that might be a little bit messy. You can go back and rewind the video, watch any parts again that you might want to do. If you have questions, or even if you don't have questions, you ought to go back and reread the appropriate sections in your textbook that deal with representation of substances. You should work any study problems that you have on this section. And then once you've done those things and you feel like you've got this down pretty well, then move on and watch the next video. And I will see you in class.